move to the next speaker, Nilanjandev Bhaumik. Nilanjan, can you share your screen?
Okay, I can share the screen. Am I audible?
Yes, you are. Just speak a little loudly, Nilanjan.
Okay, okay.
Yeah.
Is it okay?
Yes, it's better. Yeah.
My cursor is also visible, right?
Yes, yes.
Okay, so we'll have 12 minutes for your talk and 3 minutes for questions. At 10 minutes, I will let you know.
Okay, I will start then. Okay, so first, let me thank the organizers for giving me the opportunity to present here. I'm a PhD student at IISc Bangalore. I'm working with Dr. Rajiv Kumar Jain. Here we study the formation of primordial black holes and the induced GW background coming from a single field model of inflation. And we focus a few aspects of reheating.
Nilanjan, sorry to interrupt. Can you come closer to the mic?
Okay, is it better now?
Yes, yes. Thank you.
Okay. So this is a brief overview of my talk. First, I will discuss the primordial black hole and GW background coming from ultra-slow roll models of inflation. Then I shall go to the reheating effects. In the first day, Professor Klese has already given a nice overview of primordial black holes. As he has mentioned, primordial black holes have gained a recent renewed interest after the GW detection in LIGO Virgo Observatory, coming from very massive binary black hole mergers. Now, if we look at this plot of primordial black hole contribution to dark matter, this is constant differently at different mass ranges. These microlensing constants are, of course, subject to different astrophysical uncertainties and also the clustering history of primordial black holes. But at least there are this mass range, namely the asteroid mass range, where primordial black hole can contribute to the totality of dark matter. Now, if we consider different mechanisms of primordial black hole formation, inflation is actually the most natural one. The quantum fluctuations during inflation can be directly related to the CMB anisotropies at large scale, and so therefore are quite constant. But if we consider the small scale, there the quantum fluctuations can grow to lead to the formation of primordial black hole. In this plot, the moving horizon size during inflation decreases, and in post-inflationary phase, it starts to increase. So the scales which exit the horizon during inflation will re-enter at a later stage. The larger scale will exit the horizon earlier, but re-enter later. The scales of our interest, the PBH scales, that will exit the horizon at a later stage of inflation, but enter at early radiation domination. Now the perturbation modes corresponding to these scales, if that has sufficient amplitude, that will collapse to form primordial black holes just at the re-entry during radiation domination. Here we take a potential like this with inflection point conditions, where inflection point condition will provide a flat part in the potential corresponding to the ultra-slow roll phase that will lead to the amplification of curvature perturbations. In this plot of two-point function of co-moving curvature perturbation R, which follows the Mukhanov-Shashik equation, you can see that changing the location of inflection points, it is possible to amplify the perturbations in different wave numbers or different length scale. That will in turn correspond to different mass ranges for primordial black holes. As you can see, it is possible to form also in asteroid mass range to contribute to the totality of dark matter. Now, whenever scalar perturbations are amplified to produce primordial black holes, these perturbations will source to tensor perturbation at second order following this equation and lead to amplification in secondary GW background. In yesterday's session, Raghavendra and Guillaume Domenech has discussed this effect. So now if we look into the expression of energy density per logarithmic wave number interval, you can see this last term is coming directly from the inflationary scalar perturbations, while the second last term, the kernel term, will reflect the evolution of scalar perturbation during post-inflationary phases. So that will lead to the amplification in the GW background at a frequency inversely proportional to the mass of the primordial black holes. Until today, there has not been any confirmed detection of stochastic GW background. There is a claim from Nanograph which falls in this frequency range. But in recent future, the detection of stochastic GW background is anticipated in various different frequency ranges from different observatories, as you can see from these sensitivity curves. So when these observations come along, that will constrain our model parameters significantly, and also the other PBH forming models. One interesting aspect of this class of models is the tension of scalar index. As you can see in this plot of scalar index ns and tensor to scalar ratio r, as we go to form higher order, higher mass primordial black holes, the tensor to scalar index decreases rapidly, leading to a tension with Planck 18 data. So we can say that in these class of models, lower mass primordial black holes like asteroid mass or even lower mass are preferable. Like if we consider a primordial black hole of mass range 10 to the power minus 20 or 21, that will evaporate even before matter radiation equality, so will not contribute to dark matter, but still it can lead to observable imprint in the like detectable in LIGO. For the next part of my talk, I shall focus on non-instantaneous reheating histories and effects coming from it. I will restrict myself to a very simple model where the equation of state will be W reheating and the equal duration will be N reheating. As you can see in this plot of Hubble horizon, during inflation the Hubble horizon stays constant. Then it starts to increase during radiation domination, matter domination, and dark energy domination. So if we have a intermediate reheating phase between standard radiation domination and inflation, this slope is changing, and this change of slope will lead to a different energy scale of inflation, which is basically the height of this horizontal line. And it will also change the time at which inflation is ending. So all the scales during inflation will be remapped due to a non-instantaneous reheating history, which can be represented with a formula like this. This remapping will reflect also in the perturbation modes. Here in this power spectra plot, you can see the black line coming from the instantaneous reheating history, where the orange line is coming for a prolonged matter dominated reheating phase, where the peak is at a lower wave number. This in turn will also affect the primordial black hole mass range. Compared to this black line, for a matter dominated reheating history, we shall have a primordial black hole formation at higher mass range with higher abundance, as you can see. Now if we want to consider the reheating effects for GW background, the effects are basically twofold. The first effect will come due to the remapping, and this effect will be encoded in these last two terms. But also there will be another significant effect coming due to the kernel term, the second last term. This effect is coming due to the non-trivial evolution of scalar perturbation modes during the reheating phase. If we consider a early matter dominated reheating phase, it is possible to show that we can neglect the GW generated during matter domination. That will be a subdominant contribution compared to the contribution coming from the radiation domination. But even then, the radiation component that we calculate, that will be altered due to the presence of a early matter domination. Here we take the conformal time for the matter to radiation transition as eta r and introduce a dimensionless parameter as a product of conformal time and wave number k. And we can see the kernel term will depend both on the scalar transfer function tau and its time derivative. In this plot, we are plotting the transfer function for three perturbation modes. The red one enters the horizon during late radiation domination. The black one enters during matter radiation equality, while the blue one will enter at early matter domination. And we can see compared to other modes, the blue one drops very quickly at exactly matter to radiation transition point, and it oscillates with quite a larger amplitude and frequency. This oscillation will source
minutes.
Okay, I'll complete. So these oscillations will source these time derivative terms in this expression and lead to an amplification in the GW background, a secondary amplification at a higher frequency, other than the primary amplification coming due to the primordial black hole formation. Usually, when we consider the present day energy density of GW, we take different oscillatory terms and take a late time oscillation average. In the kernel level, it is possible to decouple this effect. If we take the lowest order contribution, that will reproduce the instantaneous reheating results. And if we go for a highest order contribution, that will contribute to the second peak. Now, combining these two results, we will get a picture like this. The black line shall correspond to instantaneous reheating phase, while if we consider a matter-dominated reheating phase with default duration 10, we shall get a curve like the orange one, where the frequency will be lower, the primary peak frequency will be lower, and we will also have a secondary amplification. We also consider two different primordial black hole mass range, keeping the reheating history fixed, and we get a plot like this. So you can see changing the primordial black hole mass range will change the primary peak frequency, and the amplitude of the secondary peak will also change. So the amplitude of the secondary peak will depend both on the reheating history and also the proximity of the primary peak. So now I will summarize. It is possible to form primordial black hole and generate GW background from these class of models. Here, the lower mass primordial black holes are favored due to the NS tension. Whenever we have a reheating history, that will remap the scales, leading to a shift in the mass range of primordial black hole and frequency range of GW background. Only if we have a matter-dominated reheating phase with sudden matter to radiation transition, that can lead to a secondary amplification in the induced GW background. The amplitude of which will depend both on the nature of reheating, duration of reheating, and the primordial black hole mass range. So with that, I will end. Thanks for your attention.
Okay, thank you, Nilanjan, for the nice talk. And we have a couple of, we can take a couple of questions. Please raise your hand. Sriram.
Hi, Nilanjan. Thank you for the talk. Nice one. Nice talk. My question is, why are you assuming the reheating epoch to be matter dominated? It depends on the potential you're working with, right?
Yeah, that is true. We can assume also the other cases, but the thing is that you will not get an amplification in those cases. I will come to here in this plot. Is it visible? Like
yes.
In the transfer function plot, you can see if we have a reheating phase other than matter domination, this mode will decay whenever it enters the horizon, and you will not get here. The amplification is coming because during matter domination, the amplitude of the scalar first order scalar perturbation mode is staying constant, and it is starting to oscillate and decay just at the matter radiation equality. And the frequency of this mode will definitely will be proportional to its wave number, and which will be quite higher to the compared to the Hubble parameter at the matter radiation equality. This is the oscillation that is leading to the amplification. So if you consider the other other Ws, that will not actually lead to any amplification. That is one thing.
Okay, thank you. I may have other questions, but I'll speak to you separately.
Okay, so one final question, Raghavan.
Yeah, Nilanjan, have you considered curvaton models? Because that will change that initial, the conditions soon after inflation could lead to something interesting. Or
no, we have not actually.
Okay.
That may also lead to, I think, non-Gaussianities, right?
So if there are no more questions, then let's thank Nilanjan again.